we start to the decoder block. Now in case of a decoder block, all the blocks are same as what we looked before. The only two changes are, in case of the first masked multi-head attention, because we want to be sure that we are only looking at the tokens which came before, not after, we used a masked attention. We already talked about using mask in attention blocks. So in this case, we will mask everything which is coming ahead and we will only keep things which are back. And this second multi-head attention, now that has been a communication phase done between whatever the input was, we want to do another communication phase this time, which happens between whatever the encoder learnt and whatever the currently decoder has at hand. And once this second communication phase also is done, now we have done communication between our decoder state and whatever we have learned from encoder state. And then you combine all of this together and pass it to a feed forward block. We can accumulate all of that together and give us the final outcome. So code wise, all of these are same blocks which we have used, and that is what's the great about it, that the same blocks just stacked together again and again, the same very general pattern being repeated again and again is powerful enough to be able to learn very complex sequences. So to look at the code at a decoder block level, a decoder layer now just becomes, we have our multi-head attention, we have a second multi-head attention which would be the encoder-decoder attention, we have our feed forward block, and for each of these three blocks we have a normalization layer and a dropout layer. Our forward just becomes, we pass through our first attention, we residual connection and normalize, then we do our encoder-decoder attention, again residual collection and normalize, and then we pass it through a feed forward network, we normalize it the last time, and that is our output. Everything we used in terms of the code of multi-head attention or feed forward block is everything same as which we wrote before. So that way, to code wise, this is a very efficient architecture that same blocks are used again and again. And finally, our decoder layer is again the same. You have your embedding layer, you have your positional encodings, you call this decoder block layer which we just talked about, you call it n number of times, and after each point you do a dropout, you add a same kind of positional embedding to it, and you are done. You have your decoder block. And once you have a encoder block and a decoder block, putting it all together to make a transformer is simple. You take your encoder block, you take your decoder block, and you have a fully connected output. This is one will take your decoder output and would pass it through a softmax to give you like a vocabulary level softmax. So how generation normally works is, as in previous sequence to sequence model you had seen, if you have vocabulary of let's say 10,000 words, you will just do a softmax on 10,000, you would have output layer with softmax of 10,000 size, and each neuron would represent one word, and whatever the word which have the highest probability would be the next generated word. And of course there are complexities like you can do it better using beam search, which are out of the scope of this lecture. But yeah, so a forward pass it, you pass your input through encoder, you pass your input and you pass your source mask. This source mask would carry information about like padding information. So here you see a small function which creates the source mask. Here I am seeing whatever is the padding index, just mask it as put a mask there. And then your decoder layer would get the output of your encoder block and your target mask, and this target mask is slightly more looks like more complex, but if you look at it, it's very simple. First, of course, we want to mask everything which is a padding index, and second, we in our entire mask, because we only want to look at things which came before and not after, we take our entire upper triangle and just mask it, and then we are just doing a AND gate, which is okay, there is a masking based index, there is a masking based, there is a padding based mask, there is a I don't want to look forward based mask, and we want to do AND gate on both, that if anything is masked in any of one of this case, it become a mask, and then we pass that together. And that is as simple as what transformer looks like. You can try running this code. I run it on a very small sequence. Of course, right now we are not training this network, we are just doing a forward pass. Once this forward pass is done, so we started with the source and target vocabulary of 10,000. We named our model dimension to be 512 and number of heads to be 8 because it needs to be divisible. In this case, each head would have a embedding of 64. We kept talking about this feed forward block in encoder and decoder, which has 2 layers. The dimension of that feed forward is 2048. So what would happen is 512 would go in, it would go from 512 to 2048, and then the second layer would bring it back from 2048 to 512 again. We are going to have 6 encoder and decoder layers, and the maximum sequence length is 100. Yes, and if you see, finally you have output layer of a 32 is our batch size, our maximum sequence length is 100. We started with a batch size of 32, which is we want to look at 32 sequences at the same time, 100 size each, and eventually your output is 3200 for 10,000. So which is your softmax output. So for each batch, for 100 sequences, sequence length, and for each sequence point you have a softmax done to present, okay, at this sequence this needs to be the word. Of course, this model now needs to be trained. It can be trained on different tasks via calculating a loss and back propagation. So here we are not training the model, but we have created the code for an entire transformer block to do it from scratch forward to end. Understand, while using transformer in real life world, you would not need to write all of this code. There are great libraries like PyTorch has a layer called multi-head attention, and of course which would let you do all of this in one line of code. The idea of looking at all of this code right now was so you can understand very well every small nook and cranny of how transformers as a network work. Now that we have seen the network, there are some adjacent things to the networks which I want to talk about, which would tie it all together. The first one being tokenization. What we keep talking about, there would be an input to this model, and this would be in terms of words or tokens. Here, so before sending the model in, you need to do tokenization, which is normally the step which converts the text into words. So how do we do it? You can do a very simple method, like you break the entire thing into characters. So every alphabet is a character, like you break it at an alphabet level. It has a benefit that your vocabulary size becomes really small. So if we consider the example of English, you have 26 letters, 0 to 9, 10 digits, so that is 36, maybe some punctuations thrown in. You have very small vocabulary, less than 50. However, the problem is your sequence lengths become extremely long. So for example, even for a single word, your sequence length becomes like 5 to 6. And for longer sentences, this can easily go up to in thousands. And that can be a problem. We'll talk about it later why it is a problem, but to give you a glimpse of it, transformers are doing self-attention, which is if you start with a sequence length of L, you end up with the L cross L matrix. So now for the increase in the and then you are doing it for multiple times for multiple heads. So for even a small, you are almost growing at a scale of quadruples here. So for small increases in sequence length, your score matrices would grow very fast, and that would have implication in terms of course compute, but more heavy implications of terms of storage. So let's go to the extremely other end, which is break everything into number of each word becomes a sequence. That is great that your sequence length is contained. At no point your sequence length can be greater than whatever was the length of initial text. However, the problem here is that you have a very large vocabulary now. Okay, so there have been more tokenization methods, which is a middle of both of these, where they want to still represent each thing at a word level, but maybe with some breakage. So the repetitions can be handled. So for example, think of 3 words like eating, running and reading. You can name all of these 3, but there are also so many other words which have the ing in the end. So why can't we just make ing one token and then run, eat and read 3 tokens? So every time the input is read is a token, run is a token, but when running is a token, it can be just run and ing. That way now you have just have 4 tokens: run, eat, read, and a ing, but you can represent so many words using it. Like using these 4 vocabulary size, you are able to represent run, eat and read, but you are also able to represent running, eating, reading, and everything else which would have a ing word into it. By just adding one more word, you don't need to add ing again. So you see there are some efficiency gains in taking a word and breaking it at a subword level. But how do you do is subword breakage? There are different algorithms for it. The exact algorithms are out of the scope of this lecture, but 2 of the most famous ones are word piece tokenization and byte pair tokenizations. I've added links to small YouTube videos which talk about these in great detail. I think you should go back and have a look at those. And then, now that we have seen the entire working of transformer, there has to be a conversation about why is transformer so revolutionary. At the end of the day, it started as a simple machine translation architecture. Even the original paper is a machine translation paper, it does not propose it to be this some great general architecture which can revolutionize the AI world. But today that is what exactly it has done. So we want to see why that is happening. So first is it's very computationally efficient. As we talked about, everything is a matrix multiplication, and everything, each computation step can happen in parallel. That's why when you have access to big GPU clusters, everything happens in parallel very fast. This is much more efficient than everything else, and this has generalized across domain. It started with sequences, but today you see there are vision transformers, there are speech transformers. So in a vision transformer, you take an image, you break it into blocks, and then you pass it those as tokens. And the idea being that each block captures some part of the image, and then there can be attention between these blocks. But why is this so generalizable? I think transformer reminds me of this old essay which I really like, which is called The Bitter Lesson by Professor Rich. He was one of the biggest founders, he was one of the initial pioneers of reinforcement learning, and you should go back and read this essay. But the argument which he makes essentially in this essay is that AI over decades have seen this cycle where we come to a problem, let's say the problem of playing chess. Scientists would put immense amount of effort in trying to come up with very intelligent methods to encode how to play chess. Like, you know, they will come up with interesting rules and interesting algorithms which can encode clever methods of if this is done, do this, if this is done, do this. But eventually what happens is that thanks to Moore's law, compute goes up, memory goes up, bigger data set comes in, and eventually a very general search kind of method would be able to outperform all these intelligent techniques which have been built, because they would just be able to search through a very large subspace. And the only thing which is stopping us from doing it today is we don't have enough compute power. And we have seen now that compute power keeps on increasing year on year. So his argument was, and this has been seen repeatedly, when trying to encode sequences. There was a time when sequences used to be encoded by at a word, at a phenome level, using hidden Markov chains. Then came RNN kinds of structure, then came attention, and now attention. In fact, so their argument is that eventually there would be very general and scalable systems like search, which would be able to capture better information than any smart encoding knowledge feature we would be able to come up with. And what AI model should be aimed to do is, instead of trying to encode intelligent structure, make very scalable and intelligent search and search algorithms, which can then go and in the process of learning in itself find the intelligent structure itself. So we do not need to encode everything which humans know. We just need to encode the process of searching in the model, and the model would go and find intelligent structures, even maybe much better than how humans can do it. And that is the argument he makes, and he calls it a bitter lesson because it's a bitter lesson because the inherent urge in as a problem solver is to come out with the elegant solution which can solve the entire problem. You don't want to build a solution which can go ahead and find the solution. But this has repeated again and again that we'll come up with elegant solutions. They'll give us some benefits in the short term, but eventually when compute goes up, a larger data once we can compute on larger data sets, those generic methods would outperform. And transformer is one of the greatest example of that. Transformer took away a lot of the frills which we had encoded over time, and it came down to a very generic search method, which is what we call attention. In fact, a very interesting story is that the initial attention, not the attention is all you need paper, the vanilla attention, which used to take your current decoder state and used to go back to all the hidden states and look back at each of the vector to see what is important. Again, you see, this is a kind of search. You take whatever query you have right now, you go back and look at each of the hidden state and see what is important, and that's where the terminology of query, key and value comes in. This is coming from information retrieval, where you do build search system, and the initial name, because they were going back and searching, was supposed to be RNN search. But when Professor Yoshio Bengio, being part of the project, he looked at the mechanism, he named it attention because, and he thought it's a better name. Otherwise we would have RNN search is all you need today. But so you see, it's a very generic search method, and because it's very scalable is what has led to transformer becoming what it is, where today, irrespective of what modality of problem you are solving, whether it's video, whether it's images, whether it's genome sequences, whether it's graph, and of course language, everyone is almost using a transformer architecture because it's so general that it scales so well. However, there are limitations to transformer. One of the biggest limitations, as we talked about in when we are talking about tokenization, is high memory usage. Even though the compute is very efficient because everything can be done in parallel, the memory usage are extremely high because they quadruple with multi-head attention. Because if you had L cross L, as the sequence length goes up, you are increasing it by square, and then you have multiple heads themselves. Okay, so memory usage goes up extremely fast. So in the recent times, if you would have seen the announcements of these fancy models like ChatGPT 1, then ChatGPT 2, 3, 4.0, one of the common improvements you listen to is now it supports a context window of this length. Now it supports a bigger context window of this length. This is that context window, that because the context window is the limitation of how big of a matrix you can hold in memory, and there are other problems which comes with having very large size matrices. They name it as a development because they have figured out methods of supporting larger context windows, but that is one of the biggest limitations of transformer today. Of course, this being a very general method, which the benefits of general method is they can get to very great state of performances. However, trouble of doing that same is that unlike trying to encode very interesting and nuanced structures, in this case you have to just throw a lot of compute and a lot of data at it and it would come out with very great answer, but this can't be done with very limited amount of training today. So all of these great transformer model outcome models, you would generally see they are trained of hundreds of millions, sometimes even billions of sequences for large amount of times. These are two of the biggest limitations of transformers. And finally, now that you have learned transformer, we talked about how this is what leads to fancy stuff like BERTs and GPT and everything else. So we're going to talk about the two most common one in case of language, the BERT and GPT. BERT is you just take the encoder part of it, and because BERT is not a generation model, BERT was a model which is a very good encoder model. The idea being that any given sequence, it can be encoded and then it can be used for multiple downstream tasks like sentiment analysis or your profanity detection or anything else. And because it does not need to generate, it doesn't have a decoder part, they just take the encoder block, they train it using different tasks. In the case of BERT, it was masked language modeling and next sentence prediction, and the idea is you have a big attention encoder block. Similarly, GPT, this being the initially being a translation architecture, there was a original language which got encoded and then led to generation is done in the second language. But a typical GPT is not trying to translate. A typical GPT is just given an input would generate the input ahead it. So it does not really need an encoder block. It just needs to do the searching between whatever past context it has to generate the forward context. So because it does not need an encoder block, they ditch the encoder block and they just take the decoder block, and that is what we call GPTs today. And that's why you would hear the terminology of GPT is a decoder only model. That is where it's coming from. With that, we come to the end of the lecture. Just to recap everything quickly, we talked about transformer, which seems to be this new model which has taken everything by storm. It's a very simple architecture, at the heart of which is a self attention. Self attention is doing the process of attention but within the sequence itself, so we can figure out what are the relations in the sequence itself. When you do it in parallel, it becomes multi-head, and this has a great power of that the sequence communicates with every part of the sequence itself and gives you this finally that what is important and what is not. And this importance information or communication phase information gets passed through a normal feed forward block to put it all together, and that is what our encoder does. And then the same process repeated in the decoder stage, although with some changes of two attention head, one within itself and one with the encoder block, and this together repeats itself to build the entire transformer architecture together. We looked at the source code for each of this process. I would urge you to take some time, play around with code, and that would lead to an even better understanding of how everything works. And finally, we talked about how tokenization works, how there are more advanced byte pair and word piece level tokenization, which gives us more efficient tokenization methods. How transformers are so generalizable, and that is what makes them so revolutionary, like how today for each modality transformers are used. And we ended with how we can use an encoder only block, and that is what eventually led to what we know as BERT today, and a decoder block can be used for GPT, and another example of how scalable and generalizable these networks are. Okay, thank you. I hope you got the understanding from this lecture. Thank you.